So today we're going to be going over questions for financial mathematics. So our first question is, Tyler graduates from college today and turns 20 years old. Starting 1 year from today, Tyler makes level annual deposits into a savings account that pays 4% per year. How much would Tyler need to deposit at the end of each year to have $1 million on his 65th birthday? So one thing we can notice off rip is it's starting 1 year from today. So since it's starting 1 year from today, that tells us it's going to be immediate, annuity immediate, not annuity due. We can also notice that it gives us our final value of $1 million, which means that we're going to not be looking for present value, but we're going to be looking for accumulated value. So setting this up, we know that we want to figure out how much he needs to deposit at the end of each year, which is what our X is going to be. And then we're going to have our rest of our formula just like our regular accumulated value formula, which is going to be our S, and our amount of years from 22 to 65 is going to be 43, and we're going to be at a 4% interest. And since this is accumulated value, we're going to set this to our final value, which is going to be our $1 million. So now we want to solve our S, which we can just use our regular formula. So we'll have X, and this will become 1 plus our value of I, which is 0.04, to the power of our N, which is our 43. And then we're going to subtract 1 and divide it all by our interest, which is 0.04. And we're going to set this equal to 1 million. Now from here, we're able to simplify what's inside of our bracket, which was our S value. So this is going to become X, and just put this into your calculator to give you 110.012382, and this is going to be equal to 1 million. Now from here, to solve for X, all we need to do is divide both sides by our 110 to give us X being equal to, always make sure to add the money sign, $9,089.89. Next up, we have question 2.2, which is Paul expects to receive payments of $1,000 at the end of each year for 5 years, with payments to start 1 year from now. Howard expects to receive payments of X dollars at the end of each year for 10 years, with payments to start 1 year from now. At an annual effective interest rate of 5%, the present value of the cash flows are equal. Determine X. So the first thing we're going to do here is we're going to set up the present value for Paul. So using present value, we know that we're going to be using our A formulas, not our S formulas. And as well as we see that they's saying at the end of each year. So we know that we're using annuity immediate, not annuity due. So now from here, what we're able to do is set up our Paul equation. So he gets $1,000 at the end of each year, so 1,000 for 5 years. So we're going to have our annuity for 5 years, our N is 5, and our interest is 5%. Now, we're going to set this equal to our formula solved. So we're going to have 1,000, and our A is really just going to become 1 minus 1 plus our interest, so 1.05, to the power of negative n. So negative 5, all divided by our interest, which is 0.05. So now solving this gives us 1,000 multiplied by 4.329,477, which simplifies to $4,329.48. So now what we can do is we already have our answer for Paul. So now we notice that for 5 years for Paul, the present value is the same for 10 years of Howard. So using our answer from Paul, we're able to set it up where we have 4,329 with our 48 cents, and we're going to set it equal to our X payments for Howard because we don't know what it is, but the annuity for 10 years this time was still the 5% interest. So following the same steps as before, we can just solve our annuity. So we have 4,329.58 is equal to X multiplied by 1 minus 1.05 to the power of negative 10 this time, because our N is going to be 10, divided by our interest, which is still 0.05. And now all it is solving for X. So first we'll simplify to make it 4,329.48 is equal to X multiplied by 7.721735. Now solving for X, we get X is equal to 4,329.48 divided by 7.72, which gives us 560.69. And now one way to test this is, since we already have our present value for Paul, what we're able to do is just test our present value for Howard with our new number. So we're going to have 560, and we're going to have our A 10 and 5%. So this is going to be equal to 560 multiplied by our 7.721. So we get 7.721735. And now putting this into a calculator, we'll have 560 multiplied by 7.721735. We'll get 560.69 multiplied by our 7.721, which gives us 560.69 multiplied by 7.721735, which we can see will give us the same answer, being $4,329.48. Now next up we have question 2.3, which says that starting today, Matt receives payments of $20 at the beginning of each of the next 3 years. And starting 3 years from now, Matt receives payments of $10 at the beginning of the next 3 years. The annual effective interest rate is 8%, and we want to calculate the present value of these payments. So the first thing we can see is that it says the beginning of each year, which means we're going to be using annuity due. Annuity due instead of immediate. And also we're looking for present value, so we're going to be using A formulas, not S formulas. So there's 2 ways to do this question, and we're going to do them both ways just so you can see each way. So the first way is solving for the 3-year annuity due. So for the first 3 years, he receives payments of $20 at the beginning of each year. So what we're able to do is kind of split this up, because we can see if we draw a timeline for 6 years, with the first way we're having $20, which we could technically split up to 1010, 1010, and 1010. And then on the last 3 years, it's just single tens. So one way we could set this up is just by having a $10 going to 3 years, as well as a $10 going to 6 years. So the way this would work, this will have 10 multiplied by the annuity due, with our n being 3, because this is our 3-year one, at 8%, and then we'd add 10 times our annuity due, but this time it would be 6, which is our remaining 6 at 8%. So solving this, we could get 10 times our annuity due, which is 1 minus our 1 plus I to the power of negative n. But since it's due, it's not going to be divided by our I. It's going to be divided by d, which, if you remember, d is equal to I over 1 plus I. So this is going to be divided by 0.08 divided by 1.08. And this is going to be added with 10 multiplied by 1 minus 1.08 to the power of negative 6, all divided by, again, our d, which is going to be 0.08 divided by 1.08, which gives us, when you simplify this into a calculator, it will give us 27.83 plus 49.93, which gives us our final answer of 77.76. Now, the other way we could do this is by keeping our payments at a 20. So we'll have 20 and our annuity due at 3 with 8%, except this time when we add it, we're going to add 10 with our annuity due, and it's only going to be 3 years, because this is the only 3 years that we're worried about, with 8%. But since we started 3 years from now, and it's annuity due, we have to multiply the second term by v to the 3, since that's the 3 years in the past that we're missing. However, if this was annuity immediate, so this was just regular A, 3 and 8%, instead of multiplying it by v to the 3, it would be v to the 2. But we're not worried about that right now. So now from here, what we're able to do is we'll get 20 multiplied by our A, 3 and 8, which we know from before is 1 minus 1.08 to the power of negative 3, divided by 0.08, divided by 1.08. And now this is going to be added with 10 multiplied by 1 minus 1.08 to the power of negative 3 again, divided by 0.08 divided by 1.08. And this is all multiplied by v cubed. And if you remember, v is equal to, similar to d, but except it's 1 over 1 plus I. So it's going to be 1 over 1 plus I, all cubed. So now putting this into a calculator, we'll get 20 multiplied by 2.783 plus 10 times 2.783265 multiplied by 1 over 1.08 all cubed. So now this will give us the exact same as before, being 77.76.